send it to the cloud. And I think that means we started. Okay. Hello, hello. Welcome to the Monday seminar. I'm Chris Marone. I'm super happy to see you all here and to welcome you to this seminar that's been going on for a few years. It's completely informal. If you happen to be new to it, please join the mailing list about it, and you'll hear about the future ones, as well as have access to the recordings of previous ones. We have been incredibly lucky over time to have people like Sadegh who've put together for us and don't mind doing it by Zoom. There are, as you know, many detractions from doing things by Zoom. One of them is that poor Sadegh probably feels like he's just in his office by himself talking to his screen. So, let's interact with him. One way that you can do that is by interrupting with points of clarification along the way. There's lots of time at the end for questions and discussion, so save the important and the complicated things until the end. With that, again, reach out and thank Sadegh for being with us and turn everything over to him.
Yeah, thank you, Chris, for inviting me and having me here, and thank you all for being here for this talk, which is about temporal evolution of seismicity. And I will show you some results from lab scale to tectonic scales, and usually the methodology is based on machine learning algorithm. For sure, the results are the outcomes of several years of teamwork and collaboration with many other researchers. You can see the names, so I don't read them, but most of them are well known. Let's go to the let's go to the topic, which is temporal evolution of seismicity, which is a kind of general, let's say, concept. And it refers to the changes of frequency, magnitude, and spatial distribution of earthquake over a time span and over a specific area. So the kind of most well-known example would be the spatiotemporal migration of even locations, or whatsoever a characteristic of seismicity that one can use. But here today, I will show you some results both from seismicity catalog and seismic waveforms. And from seismicity catalog, I will use the experimental data from lab scale, extract some features, and I will try to find some clusters using unsupervised learning. And then I will show you some other results that how we somehow upscale the same methodology for the tectonic scale, but again, we extract some features out of the catalog, but here we try to summarize all features per each family of events. And then finally, we used unsupervised learning to find the clusters or categories. And on the second part of my talk, I will show you some results based on the seismic waveform. So by seismic waveforms, the idea was to somehow compare the waveforms relative to each other, but we used the seismicity of the central Italy and the SciSLM Foundation model to extract some features, and we tried to work with the features to find some temporal changing in seismicity. Before going further, I need to mention that the word of clustering, we have it in two different kind of literatures. Seismic literature, we use clustering analysis and background clustered seismicity, which is very well known to us. And on the other hand, in machine learning and statistics, we also have unsupervised clustering. So to not mixing the word of clustering of seismic literature and statistics, I will use the clustering for the seismic literature. And whenever I use clustering, I mean a clustering analysis, background cluster seismicity. And for the machine learning part, I will try to use category and categorization just to not mix the word. Okay, let's start with the experimental setup. I'm pretty sure most of you are familiar with the 3D six-slip experiment of the rock with the notch samples. You can see that the sample is cut in both sides and it's put in the machine. and the fault surface is generated inside the machine. So we put the sample in the machine, increase the axial stress, and the fault surface is generated, or the sample is broken inside the machine, which is believed that the fault zone and fault surface is very similar to what can happen in reality for a rock. And after that, we increase the axial stress, and then there will be lots of stick slip from small to large slips. And during each slip, we have several or many acoustic emissions that we can record them using these acoustic emission sensors, which are glued around the samples. So you can see that every tiny event can be recorded in different channels. And by this information, so we can find the first arrivals of each event in each channel. So we can compute the location of each event, the magnitude, and we have also the time, which means that we have access to the catalog of seismicity, acoustic emission seismicity, and which in our case we had access to the three samples of Sadegh granite, sample 4, 5, and 7, with more than 500,000 of events. So, here's a very nice kind of video from Grzegorz Kwiatek. You can see from the upper side, which is the stress change, and you can see each cycles and the slips. And at the same time, you can see the seismicity pattern on the fault surface, that how it changes, how it evolves from the starting of a cycle to the end of each cycle. So for sure, there are some different characteristics or different seismicity pattern. And the idea is of us is to find these characteristics using catalog-driven features. So the first step is to extract some features out of the catalogs, and especially these features were driven by, or were extracted by Grzegorz Kwiatek, and it ranges a lot of different characteristics like event rate, Gutenberg-Richter p-value, correlation integral, to clustering features and whatsoever features that you can see here. And we can also compute each features in different time windows. So small time window means that we are interested to see the feature values in very tiny time window, small details. But large time windows means that we are going to see the general variation of that features. So on the right side, you can see some examples for sample 4 for event rate, p-value in different windows and the other features. So when we have our features, which is like 47 features in this case, we use these features as the input, and we want to use unsupervised learning to find some different categories. And to do this, we use K-means algorithm with 3 number of categories. And the idea is to find some categories of seismicity based on these features that are different from each other, but internally they are similar in each case. So the output of this K-means categorization, let's say, is 3 categories that we try to use stress values and color-coded them by these categories, just to show that if there is kind of a meaningful relationship between these categories and the stress value or not. But note that we did not use the stress value at all. So the model has no idea about the stress and only uses the features to extract these categories. And interestingly, you can see for all 3 samples, all cycles starts with green category and ends somehow in most of cases with the red category, which is in kind of very well agreement with the mechanical behavior of rock in each cycle. So if we look at the seismicity pattern in each category, we can also see that it's obviously they contain different somehow seismicity pattern in each category. So the main message of this study was that the catalog-driven features could give us some information about the dynamic of the stress and the stress level, and we can use it to somehow track or monitor the seismicity evolution. So this was somehow a motivation for us to upscale the methodology from a lab scale to the field scale, because all we use is the catalog of seismicity, basically. So we could imagine to somehow upscale all the kind of flowchart to a field scale, and we wanted to test how we can track or monitor the seismicity using this methodology. But before going to showing the results, we decided to somehow enhance our methodology, or let's say the flowchart. So in the first step, for feature computation, unlike the laboratory case, here we computed the features per each event, for each event. It means that we know. Yeah.
Sorry, it's Chris. Sorry to interrupt. But could you, like in the 1 second interval that you talked about for the lab data, I suppose that's a long time for a lot of the things that are happening. How much does that cut down with your 500,000 events? Like you're averaging over 1 second, but you must have thousands of events per second in some cases, right? Or not?
Yeah, but here in laboratory case, we compute all features every 1 second.
Okay.
So we have like a different time window, let's say a window of 100 seconds. And this is a kind of moving window, and it moves per second. So we compute, for example, B value for each second, and all events that happens in this 100 second of window, we use those to compute the B value, event rate, and whatsoever features that we have.
I see. Okay, thank you.
So we use the kind of the same idea, but here we try to use each event as a source of kind of feature computation, because we know the time and location of each event. We can define not only a time window, but also a spatial window around the location of the event. And this time, all those events that are inside the time and space window are kind of the events that we use for computing the features, and we can compute like event rate, B value, clustering features, and whatsoever features for using these events in this blue area, and assign those features only for this specific window, this specific event. So each event has its own pool of features, so we can kind of move to the next event and next event, and we can use different time and space window and compute those events per each event. And at the same time, we can also do a kind of background clustering analysis to find clustered events and background events. And we do that to remove the background seismicity. And in step 2, you can see that we only preserve the clustered seismicity, and using the nearest neighbor distance, we can find the kind of parental-child relationship between the events. So each set of events can form like a family of events, and we call each of these events as one family. So we have several families, and at the same time, on step 1.1, we have computed for each event one set of features. So each member of these blue family have its own features. So we decided to somehow find an average value of features for each family. And you can see in step 3, we assign for each family a set of feature values, which is kind of the average of its members. So now, instead of a kind of huge number of seismicity, we have a small number of families that we are going this time to use unsupervised clustering to find different categories or different seismicity patterns among these families. So we call these features as per family features, and this kind of categorization to assign to each family of events. So let's see some examples and some results. So the first one is the 2023 Kahramanmaraş earthquake. Again, you're familiar with that. This is a map view of event distribution. And the catalog is the enriched catalog by machine learning from Sebastian Nunes-Jara. And yeah, as I mentioned in the flowchart, we extract or we found the clustered and background seismicity based on the clustering analysis. And here you can see the distribution of the events in time. We have a catalog from 2017 up to the occurrence of the large earthquake. So the small gray dots are the background events, and the colored ones are all families with at least three number of family members or three members. And we also, you can also hear in this plot the families with more than 100 events, which shows a high kind of seismicity activity in 2018 and also in the preparatory phase of the major earthquake. So to use K-means algorithm, we need to specify the number of categories. Here we use the elbow plot of WCSS distance or criteria. I will show you I will expand this criteria in next slides. So simply speaking, whenever this distance decreases or show changes from one category to another one, or by adding another category, it's meaningful to add a category. But as long as adding a category does not show a high difference, it means it does not make sense to add more categories. So simply speaking, here you can see that the optimum number of categories is 4 number of events, 4 number of categories. And based on 4 number of categories, we use the K-means algorithm to find different somehow categories in our families. And the upper plot is map view, and the lower plot is, or the middle plot is the time view of the same families. So we can see that some categories are noun, but the point is that K-means is not like a physics informed algorithm, and it has no idea about the criticality or about the physically difference between these categories. So it's the expert user who should go through the details to find some kind of difference between these categories. And thanks to the features that we have, we can do it easily. And I will show you what we did here in this example. So based on our kind of background knowledge about the physics of earthquake, based on the observations in lab and also tectonic scales, and also physical models of the earthquake, we know that whenever the event rate is increased, we have, let's say, a more critical situation or state rather than when it's small. So we can look at the feature N, and in this feature, this blue color shows somehow more critical than the others because its event rate is so high. So the B value, whenever B value is small, it shows again more criticality rather than the others. So again, if we look at the BP or B positive in this case, again, the same color shows more criticality rather than the others. And we can also use correlation integral, which is the spatial localization of the event. And whenever it's high, it shows more critical, more localized events. You can see that with different kind of spatial window, the most critical category among these 4 categories are this blue color. And also we can use nearest neighbor distance as the kind of localization in time, normalized time, space, and magnitude, and also clustered seismicity, to find the most critical, let's say, category. But note that all these categories are clustered families. So relative to the background category by itself, all of them are somehow more critical, but we are going to somehow compare these four categories relative to each other, and we do this using the most well-known kind of features as I explained here. So based on this, we assign some more meaningful colors or more related to the criticality to these categories, and you can see that now they are ranked from green to red, from less critical to more critical features. So with this change of color, if we look at the map view and also the time view, we can see that the most critical color or category just happened in the preparatory phase of the earthquake. The orange, which is a bit less critical, you can see it in the preparatory and also in 2018 with a very large family of events, and the others are somehow less critical than these two categories. So it was quite interesting results, and we decided to somehow extend our this kind of workflow to see the results in different cases. And here I just show you some results, and I don't go through details, and this is only the last results, but the whole flowchart is the same. So this is the 2014 Iquique earthquake, the map view, and also you can see we used in the time plot, we used the seismicity from 2007 up to the earthquake in 2014, and almost in all years we can only see, first of all, small number of families, but all of these families are less critical than those families that can happen during 2 weeks before the large earthquake. So if this is a zoom view of 2 weeks before of the earthquake, and you can see that based on the same kind of scenario, we first detected the most critical and less critical families and used the coloring to show them, and we can see that all those families happens in the preparatory phase of the earthquake, showing that they show very distinct kind of seismicity characteristic relative to the other families happened in last several years in this region. This is another example, which is 2009 L'Aquila earthquake. And also you can see the map view and the time view. Again, we used the catalog data from 2005 up to the 2009, the earthquake, when earthquake happened. And again, we can see that most of those critical phases or let's say categories happens right before months before the earthquake, and the red category just right before the earthquake, like 1 month before the earthquake. And we also tested on some other cases that there is no preparatory phase, at least in seismicity. And to be honest, because all this flowchart is based on seismicity, so whenever there is no criticality in seismicity, it shows no criticality, okay, which is a kind of correct answer. So I will show you here the 2016 Amatrice earthquake that somehow we all know that there is no seismic kind of preparatory, non-preparatory phase for this earthquake. And if we look at the months before the earthquake, we can see that again this flowchart did not find any kind of criticality in seismicity pattern. The other example in this class is the 2024 Noto earthquake, which again is a kind of more swarm-like had swarm-like seismicity, and again the main 7.5 main shock did not show any critical seismicity. There was a kind of 6.2 magnitude earthquake in 2023 that we can see that the aftershock of that earthquake is kind of categorized as the most critical one, which is somehow sensible with a high, let's say, localization and high rate. But afterward, the flowchart cannot see any kind of criticality in seismicity, which is again because this earthquake was based on the fluid flow and fluid migration. It's kind of sensible to see the same results. But one more point here, one more important point here is that in all cases we know the location or the time of the big earthquake. So the question here is that if we have no idea about the time of the major earthquake, how we can use this flowchart for the kind of future steps of seismicity. So to show you the results, before showing you the results, I need to introduce the criteria that we used here, which is WCSS within cluster or within category, sum of a square distance, which is a distance criteria. And it's the core of the K-means clustering. So we decided to use this distance as a criteria. And suppose that in this case, this is a kind of 2D example. We have two features of seismicity, F1 and F2. And all the seismicity that we have show two different categories. So these are the feature points, and the plus is the center of each category. So we fit our model on this case, and it shows two categories. Now suppose in the next step, we have some new seismicity, new families, but they are similar to these two categories. So if we have such a situation, so the criteria that we can use to know if adding a new cluster is meaningful or not, or in other words, if we see kind of a new category of seismicity, or no, the seismicity are similar to the previous ones, we need only to compute the distance criteria for the current number of category, which is 2, and for one more number of categories, which is 3. So in this case, if we compute this distance, which you can see here, the distance, by distance I mean the distance of each event to its category center, and then the summation of all distances. So in this case, adding a new category or a new center of category does not change a lot the distance value. So for both cases, 2 and 3 number of category, we have somehow similar amount of this distance. So if we compute the delta of these two distances, the delta value will be very small. But now suppose in the next time step, Ti plus 2, we have a new category of seismicity. So what happens here is that again, we have no idea if this is a new category or the similar to the other ones. But if we compute the distance value for 2 number of categories and one more, which is 3, they show a huge kind of differences from each other. So in this case, you can see that the distances increases. So this value increase. But for 3 number of categories, this distances is small, but it doesn't matter. We need only the differences or the delta value of these two values, which increase whenever we have a new category. So with this kind of introduction, let's see the results of our cases. In each case, we use the blue area or blue time window as the training, or let's say the data that we fit the model, and the rest we test if the model needs or see a new category of a family or new category of seismicity or not. So let's just look at the Kahramanmaraş case. In this case, we use 2 years of seismicity fitted on the model, and the model can detect 3 numbers of seismicity. And then afterward, we decided to compute this criteria for 3 and 4 number of categories. So you can see that the general kind of value of this criteria stay somehow stable. We can see some fluctuations with the seismicity in 2020 and 2021, but the sharp increase just is seen whenever we kind of go to the let's say, preparatory phase of the earthquake, and there are some new patterns of seismicity, some new families that shows more different properties rather than the other seismicity. So this criteria hints us that, hey, we need to add a new category to have the best categorization, which means we have a new category of events. But again, if this new category is critical or no, again, the system has no idea, but we have access to the features of this new category. We can look at the features and compare with the other categories and see if this is a more critical category or less critical category. So if we look at the other case, for example, in L'Aquila, we can see it the kind of the general variation of this criteria stays stable, but before the earthquake, it increases. And for Iquique, again, it is stable for several years, and right before the earthquake, it increases, showing adding, I mean, the system is kind of finding new set of category or new seismicity pattern or new category, which in these cases are more critical than the others. But in these two cases, Amatrice and Noto, where we didn't have a kind of preparatory phase, you can see that the criteria stay stable until the earthquake. So this shows some potentials of this kind of framework, clustering framework, to be used or to identify the transition to the preparatory phase of large earthquakes.
Sorry, it's Chris again. I got another question. So earlier, maybe especially when you were telling us about the lab data, you had a model where you decided 4 categories was the right number. You showing us that kind of asymptotic approach to a leveling off. But now you started with fewer categories and you're looking at the jump in this WCSS. So this is what we're looking at, and maybe there's a plateau, but we're not sure.
Yeah, about the number of, because the k-means needs the number of categories. So we need to specifically say how many number of categories we need. Okay, so in laboratory case, because we had access the whole cycle from 0 to 1, let's say, when the large slip happens, we really thought about having like a traffic light system, and we asked the model to go for 3 number of categories. Okay, but here because we have no idea in where in this cycle we are, so we try to use this WCSS distance to see what is the best number of categories that we can use in our case. So when we we fit our model with this number, then for the future kind of application, we need to just go for adding one more category, if adding one more category is statistically meaningful or not. So if it's not meaningful, this criteria stays somehow stable, but if it's meaningful, it shows like a big jump here. So increasing this criteria shows that adding one more category is meaningful, and we need to add this new category, or which is somehow the new seismicity pattern.
Thank you.
Yeah. So my first part of talk is somehow finished here, and I'm going to go through the waveform-driven features. It's up to you. You can ask question, but I can also move forward and finish the talk. And then we can have the questions.
Well, there's a question in the chat by I didn't see who it's from Joan Gomberg.
Yeah. From magnitude versus template, qualitatively, it appears that the clusters begin with the largest earthquake in some interval. To what extent the clusters simplify traditional main shock aftershock sequence, for example, ETAS process embedded within the large sequence? Yeah, a good question. So because we use seismicity features, and in these features we have many features which are related to the kind of clustering features, which is the kind of the proportion of for, let's say, for each event, we have number of features, and some of those features are clustering features, and some of those clustering features are the proportion of main shock and proportion of the aftershock, which all of them are somehow calculated using the background clustering analysis. So we somehow track how much of these events are kind of locally, let's say, foreshock, main shock, or aftershocks. So these somehow features, which is called traditional main shock aftershock features, are somehow involved in this huge amount of information that we have. For example, in this case, maybe I didn't mention, but we have for each features 2 time windows and 2 space windows, which means that for each features we have 4 features, and in overall we had more than 100 features for in each case. So in this, let's say, more than 100 dimensional space, we ask the k-means clustering to find those kind of meaningful patterns, and most of them are, as we can see here, we try to sort the features based on separability. And we can see that, for example, clustered event ratio, TRP, which is again using computed using this let's say clustering analysis, and PMA is the proportion of main shocks, PAF is the proportion of aftershock, and whatsoever features. We try to somehow involve all of them in our calculations. So let me move forward to the waveform part. So for up to now, I used the catalog of seismicity, but it was a paper by Laura Laurenti et al. In 2024, published in with Chris, which published in Nature Communication, and which motivated us to look more in the waveform of the events. So they used the Amatrice 2016 Amatrice Norcia earthquake seismicity, like you can see here in the time scale, that like 2 months before and 2 months after the Norcia earthquake. And they tried to train a machine learning model to learn based on the waveform. So the input is the waveform, and they tried to train the model to differentiate between the foreshock and aftershock, which you can see in yellow and green dots here. So the results was kind of quite interesting. With a high accuracy, the model could detect between the foreshock and aftershock waveforms. And then they improved the kind of the model for a high number of classes in either foreshock and aftershock. And as you can see here, in foreshock, they have now 4 classes. In the aftershock, they have 4 classes, and 1 class here between the Visu and Norcia earthquake, which is 9 classes. And you can see the confusion matrix of the results of this classification, which shows quite a high accuracy. Note that this is a 9-class classification, and 50-50 level or guess level is like 11 or 12%, and relative to that number, 58% is quite the high number of accuracy for classification. But after this study, there was another study by Liu et al. That they presented a foundation model called SeisLM, Seismic Language Model, which you can see, and they tried to do the same kind of practice, and you can see that how much the results increase, or how this model can classify the waveform better than the other network. So as may you ask yourself, we also ask ourselves that what happened in this foundation model that it learned so kind of more information out of, or it could extract more information out of the waveforms. that it could generate, or it could classify the waveforms with such a high accuracy. So let's look at these two models. So the input is the same for both models, the 3D, three-component waveform. And the convolutional model consists, simply speaking, some convolutional layers which extract some features, and they used a kind of fully connected network as a classifier to translate these features as 9 classes that you can see the results. But foundation model has somehow the same structure, but here we can see the seismicity as the feature extraction part. Again, we have some features and the same, somehow similar classifier for the classification. But we can see very different kind of results. So if we say that the classifier parts are somehow similar to each other, the main point goes back to the features that these two models can extract. So these convolutional layers are training from scratch, specifically for the Central Italy data. But the seismicity is a pre-trained model which has been trained with more than 5 million waveform using self-supervised training, which is the kind of tokenized training of the language models. And this pre-trained model is able to extract more informative features out of the waveform that at the end it could generate, or it could find better classification in these waveforms. So what we thought was that to look at these features to find some like a track of seismicity. So we suggested to track the temporal changes in the event waveform. And for this, we needed a baseline, to choose a baseline. So we have a baseline event in our case. And then the idea is to somehow compare the other events relative to this baseline. But we are not going to do this in the kind of the waveform space, but we want to use the foundation model, extract the features, and we are going to do it in the feature space. So because events have different locations and more kind of information of the subsurface properties can be found in the coda part, we try to stay only with the coda part. So we try to use somehow similar P2S part of all events, but with different coda parts. So this somehow guarantees that the differences that we can see in the extracted features comes from the coda part of these events. We also wanted to do it without retraining. So this is a very important point. We didn't want to, because when you have these features, you can train a new model, in your case, in your region. But this limits us to apply this method for every case or every region. So we were thinking about having a more general kind of workflow, which is able to be used in every cases in every region. So we didn't want to retrain a new model here, and we want to stay fast and easy of computation. So because of that, and because the main goal is to find the differences between these events, as I mentioned, we are now looking at these features, and we want to find the differences between these two features or these two vectors. So we use very simple the distance criteria, an Euclidean distance between these two feature vectors, and we call it dissimilarity, how these features are dissimilar relative to each other. So now let's see some results. Again, we worked on the same data set that was shared by Laurenti et al., which is mainly based on the catalog by Tan et al., 2021. You can see the map view again, and you can these kind of black triangles are the stations that we used. So for each station, we computed, we extracted the features and computed the similarity. But for the baseline, we used 100 first events as the baseline. So you can see that these are different stations, and in each stations, for example, this is the Norcia station, this is the Amatrice earthquake, this is the Viso, and this is the Norcia earthquake. So we went for the first 100 events which are happening right after the Amatrice earthquake and use it as the baseline, and then find the dissimilarity of the other events relative to this baseline in each stations. So at first look, they are really distributed points, but we decided to compute a 5-day moving average value of these distributed dots, which are these black curve in each case, in each stations. But to compare them better, we decided to somehow overlay all stations together and have them together. So this is the final kind of results of dissimilarity in all stations. You can see that all stations are in color, and the mean value of all stations is in black. So here's the Amatrice earthquake, and note that we used 101st event as the baseline. So it's obvious that these waveforms pass through the most let's say damaged zone of the medium, and it could, or the baseline could show us somehow the most damaged state of the subsurface layers. So the first events show a high similarity to the baseline, so the dissimilarity is very small. And then when we move in time forward, we can see that it gradually increases. So the dissimilarity increases, which means that the new events or the new waveforms are less similar to the baseline, and they show more kind of difference relative to the baseline, which if we assume that the first or the baseline is kind of representative of the damage zone, this increase could show somehow a kind of healing in the medium. And then it's interesting when the the Viso and Norcia happens, you can see a sharp drop of the dissimilarity value, which means that again these events are very similar to the baseline, which are right after the main shocks, showing again a kind of damage phase of the medium, and then they are again gradually increase, showing somehow a kind of healing process. And we also plotted the VP values computed by seismic tomography from Claudia Chiaraba in 2020. And you can see that the red dots and the green dots are the VP value somewhere near close to the Norcia hypocenter and north of the Norcia hypocenter. So it shows that because this kind of variation in damage and healing process, we were thinking mostly about a shallow variation, which is part of the kind of changes in the waveform. But the VP value of this study shows that we can also see somehow some changes of VP also down in deeper kind of part of the fault, and which obvious shows a healing in the subsurface layer, and somehow confirm or is in well agreement with our somehow results and trends. So what are the takeaway messages or the kind of the conclusions of these studies? So first of all, laboratory study showed that catalog-driven features contain some information that could give us some information about the stress level and seismicity evolution. And the upscaling showed that we are also use somehow the same concept and flowchart to find families with different kind of or distinct characteristics. And using the criteria, the distance criteria that we mentioned, it revealed that we are also capable to somehow identify preparatory phase if there is a seismic critical information in seismicity. which if there is, then we have some potential to use such a flowchart for operational earthquake forecasting. And more interestingly, foundation models represent that they can extract some features, which at least in this one study, they showed that they are sensitive to the aftershock damage healing evolution. So honestly, my suggestion would for the machine learning community of seismic community would be to develop next generation of seismic foundation models, which would be really helpful for the downstream tasks. Thank you for your attention.
Thank you very much. That's a fabulous talk. I will invite people to unmute, turn on your camera if you'd like. Join me in thanking Sadegh for a great talk. And then, okay, let's give him a chance to catch his breath. I see that David Marcin has already put a question in the chat, and I can just invite you, David, to unmute and voice your question. Useful to use the raise hand feature here to put ourselves in order, probably. But yeah, David, if you're prepared to unmute and ask that question, why don't you?
Yeah, thanks a lot, Chris. Yeah, the question is kind of related to